Hello everyone, welcome to Neso Academy. We are learning theory of computation, and in the previous lecture, we have understood the partitioning algorithm for DFA minimization. And now in this lecture, that is Myhill-Nerode Theorem for DFA minimization, we are going to learn about the second method of DFA minimization, which is Myhill-Nerode Theorem. It is also called as the table filling method. So the topic for today's lecture is Myhill-Nerode Theorem. Let's get started. Myhill-Nerode Theorem is a method used for DFA minimization. So the first method was partitioning algorithm, and the second method, which is used to minimize a deterministic finite automata, is Myhill-Nerode Theorem. Myhill-Nerode Theorem is named after two mathematicians, John Myhill and Anil Nerode. According to Myhill-Nerode theorem, if two states behave exactly the same on every possible input string, then it is unnecessary to keep both the states. That is why we can merge those states together to form a single state. And that is the concept of DFA minimization. Myhill-Nerode theorem helps us identify whether two states of a DFA are equivalent or distinguishable, so that equivalent states can be merged together to reduce the total number of states. So Myhill-Nerode theorem helps us to identify whether the given states are equivalent states that are having the same kind of behavior, or they are distinguishable states that are having the different kind of behavior. If the states are equivalent states, they can be merged together to form a single state. And in this way, it is used to reduce the total number of states. Myhill-Nerode theorem, as I have already told you, also called as table filling method. So in your examination, you can have any of the name, Myhill-Nerode theorem or table filling method. Now, why it is called as table filling method? Because in this theorem, we use this kind of table. At every procedural step of this theorem, we will be required to mark entries in this kind of table. That is why it is called as table filling method. These English uppercase alphabets that are B, C, D, E, F and so on are the names of the states, which may change as per the question. Now let's understand how to apply Myhill-Nerode theorem to actually minimize a deterministic finite automata. So given is a deterministic finite automaton, that is DFA. So this is the transition diagram of a DFA that is given to us. And our objective is to minimize the given DFA. That is to reduce the number of states of this DFA. Let's see the procedure for Myhill-Nerode theorem. Step number 1. Remove all states that are unreachable from the initial state. So in step number 1, you need to remove all the states from this DFA that we cannot reach from the initial state of this DFA. Step number 2, draw a table for all pairs of states P, Q such that there are no duplicate pairs and there is no PP pairing. What does that mean? So in step number 2, you need to draw a table for all pairs of states P, Q. That means all the pairs of the states of this DFA should be represented using the table cells. And there is a condition. There are no duplicate pairs. That means duplicate pairs are not allowed in that table. Also, there is no PP pairing. PP pairing means the pairing of states like A, B, B, C, C, D, D and so on. So such pairings are also not allowed in that particular table. Let's move to step number 3. In step number 3, mark all pairs P, Q where P belongs to F and Q does not belong to F. That is, one state is final and the other state is non-final. So at the end of step number 2, you will get a table. In that particular table, you need to mark all the pairs P, Q where P belongs to the set of final states. this F is called the set of final states. So you need to mark all the pairs in the table where P belongs to the set of final states and Q belongs to the set of non-final states. Or we can say that Q does not belong to the set of final states. So if one state is final and the other state is non-final in that particular pair of states, then you have to mark the corresponding entry into the table. Let's see the step number 4. If there are any unmarked pairs P, Q such that the pair delta P, X, delta Q, X is marked, then mark P, Q also. What does that mean? So in step number 3, we have marked the entries in the table for the pairs in which one state is final and one state is non-final. Now it is possible that few pair of states are left unmarked. So for every unmarked pair P, Q, you need to calculate delta Px and delta Qx. And if this particular pair is marked, then you also have to mark the unmarked pair P, Q, where X is any input symbol. Repeat this until no more markings can be made. So this is a very important step of the whole procedure. And this step is to be repeated until no further markings in the table are possible. The step number 5. Combine all the unmarked pairs and make them a single state in the minimized DFA. So after that, if any pair is left unmarked, you need to combine the states of that particular pair and that will form the single state in the minimized DFA. And in this way, we will reduce the number of states of the original DFA to get the minimized version of that. Obviously, these steps will make much more sense when we actually apply these steps to minimize the given DFA. So let's start with the step number 1. Step number 1. Remove all states that are unreachable from the initial state. So this is the transition diagram of the given DFA. And I have already explained you that if we can never reach a particular state starting from the initial state of the DFA, then that state is called as an unreachable state. So starting from the initial state of the DFA, I need to check all the states. If I can reach that particular state, that is a reachable state. But if I am not able to reach that particular state, starting from the initial state, then that state is called as the unreachable state. And such states are to be removed from the DFA initially. So let's check all the states one by one. Let's first start with the state B. So we can reach from A to the state B using this particular transition. That means B is a reachable state. Now let's check C. So this transition is used to reach C from the state A. That is why C is also a reachable state. If I talk about D, then these two transitions can lead to the state D from the state A. So D is also a reachable state. Now let's talk about the state E. These two transitions are used to reach the state E from the state A. That is why E is also a reachable state. And using these two transitions, we can reach the state F from the state A. So F is also a reachable state. So we have found that no state in this particular DFA is an unreachable state. So we are done with the step number 1. Now let's proceed to the step number 2. Draw a table for all pairs of states P, Q such that there are no duplicate pairs and there is no PP pairing. So according to this step, we need to draw a table for all the pairs of states. The pairs of states are A, B, A, C, A, D, A, E, A, F. Similarly, B, C, B, E, B, D, B, F, and so on. So for all such pairs, we need to draw a table. Right now, let's ignore this further statement. First, concentrate only on this part. Draw a table for all pairs of states. So let's write all the names of the states column-wise and row-wise. First, we will write all the names of the states column-wise. A, B, C, D, E, F. These are the 6 states. Now we will write all these states row-wise also. A, B, C, D, E, F. And now we will create one cell for each pair. That is a whole table. Like this. So this is the table for all the pairs of states P, Q. Now let's concentrate on the further part, such that there are no duplicate pairs and there is no PP pairing. So first, let's focus on PP pairing. What is PP pairing? The pairing of states like A, B, B, C, C, D, D, and so on, such pairing is called as PP pairing, which means in a particular pair of states, both the states are identical to each other. And according to this step, in this particular table, we need to eliminate all the cells that are representing the pairs like this, P, P. So let's start eliminating such cells. This cell is denoting A, A. So we have to remove this cell. Now B, B. We need to remove this cell. C, C. D, D. E, E. Similarly, F, F. So these are the cells that are having PP pairing of states. So we need to eliminate all such cells. Now let's talk about the duplicate pairs. So if a particular pair is A, B, then its duplicate is B, A. So if A, B is present in the table, then you need to remove B, A from that particular table. And you need to do this for all the pairs of states. So let's start eliminating the duplicate pairs of states. So if A, B is present in the table, then we need to remove B, A. Similarly, these are the pairs that are having either PP pairing or they are duplicate pairs. So we need to eliminate all such cells from our table. And finally, after eliminating these cells, we will get the table as this one. So in examination, you have to directly draw this particular table. You don't need to draw that full table. And making this table directly is also very simple. First, column-wise, you have to write all the names of the states without writing the first state, that is A. So you start from B, C, D, E, F. And row-wise, you don't have to write the last state, that is F. So you will write A, B, C, D, E. And then column-wise, we have seen that 1, 2, 3, 4, 5. There are 5 states. So here we will draw 5 cells, then 4 cells, then 3 cells, then 2 cells, then 1 cell. And in this way, you will get this particular table. And we are done with our step number 2. Now let's proceed to the step number 3. Mark all pairs P, Q where P belongs to F and Q does not belong to F. That is, one state is final and the other state is non-final. Now in this particular diagram, we can see the states C, D and E are the final states and A, B and F are the non-final states. Now in these pair of states, if we have one state as final state and other state as non-final state, then you have to mark that pair. But if both the states are final or both the states are non-final, then you don't have to mark the entry for that particular pair. So now let's check all the pairs one by one. B, A. B and A. So you can see B and A both are non-final states. So we don't have to mark this particular pair. C, A. C and A. One is final, other is non-final. So we can mark this particular state. D and A. Now D and A, D is final and A is not final. So we can mark this particular state also. EA. EA, final, non-final. So we can mark this. One should be final and one should be non-final. FA. FA. Both are non-final. So we cannot mark this particular pair. Now let's check CB. C and B. C and B, final, non-final. So we can mark CB. Now DB, DB, final, non-final. So we can mark DB. AB, A and B, final, non-final. So we can mark this one also. FB, FB, non-final, again non-final. So we cannot mark this particular cell. Let's check another cell. DC, DC, both are final. We cannot mark that. EC, E and C, both are final. So we cannot mark EC. FC, FC, one final and other non-final. So we can mark FC. Now, ED, E and D, both are final. So we cannot mark ED. Now, FD, F and D, final, non-final. So we can mark FD. Now, FE, FE, final, non-final. So we can mark FE also. And finally, we get all the markings like this. So this is the table after performing step 3. Now let's move towards the step 4. If there are any unmarked pairs P, Q such that the pair delta Px, delta Qx is marked, then mark P, Q also. That means you need to check all the unmarked pairs. These pairs are unmarked pairs. And you need to check all these unmarked pairs one by one. For each unmarked pair P, Q, you need to calculate delta Px and delta Qx, where x is any input symbol. In this particular case, the input symbols are 0 and 1. And if, for an unmarked pair P, Q, delta Px, delta Qx, this particular pair is already marked, then you also have to mark P, Q. And you have to repeat this process until no further markings can be made. So let's start applying the step number 4 to all the unmarked pairs. We are performing the very first iteration because right now we are visiting every unmarked pair for the first time. So the very first unmarked pair of this table is B, A. So we will write B, A. Now in general, if P, Q is unmarked, then we need to calculate delta P, X, delta Q, X. And if that pair is also marked, then we have to mark P, Q. Similarly, for B, A, we have to calculate delta B, 0, delta A, 0. So we will write delta B, 0, delta A, 0. Let's calculate these two. B, 0 is A and A, 0 is B. So for this we can write A, B. Now in this table we need to check A, B. If A, B is marked, then we will mark B, A. A, B, this pair, it is unmarked. So A, B is unmarked. No problem. Let's check for the another input symbol, which is 1. So for 1, we will write delta B, 1, delta A, 1, like this. Now we will calculate B, 1 and A, 1. B, 1 is D and A, 1 is C. So we will get D, C. Now let's check D, C. D, C, this one, it is also unmarked. So both the pairs are unmarked. So we will not mark B, A. Even if one pair was marked out of these two, we have to mark B, A. So in first iteration, B, A, this pair is left unmarked. Now let's check the another unmarked pair, which is F, A. For F, A, we need to calculate delta F, 0, delta A, 0. F, 0 is F and A, 0 is B. So we will get F, B. Let's check F, B. F, B is unmarked. So F, B is unmarked. No issues. Let's check for the input symbol 1. delta f comma 1, delta a comma 1. F comma 1 is f and a comma 1 is c. So we are getting f comma c. Let's check f comma c. F comma c is marked. This time we are getting f comma c as a marked pair. So we can see at least one pair is marked. That is why we will mark f comma a in this particular table. So f comma a will be marked. And now our table looks like this. Now let's check the next unmarked pair, which is f comma b, this one. So for f comma b, we need to calculate delta f comma 0, delta b comma 0. Now f comma 0 is f and b comma 0 is a. So we are having fa. Let's check fa. fa is a marked pair. Let's check for the input symbol 1, delta f comma 1, delta b comma 1. Now f comma 1 is f and b comma 1 is d. So we are getting fd. fd, which is also marked. Now both the pairs are marked and even only one pair is marked, then also we have to mark f comma b. So we will mark f comma b. fb. This will be marked. Now the next unmarked pair is dc, this one. So d comma c. So for this we will write delta d comma 0, delta c comma 0. Now d comma 0 is e and c comma 0 is e. So we are getting ee. Now as you can see in this table, ee is not even present because initially we have removed all the cells representing the pairs having p comma p pairing. So the pairing of identical states have already been removed from this table. So this e comma e is not even present in this table. Let's check for the input symbol 1, delta d comma 1, delta c comma 1. Now d comma 1 is f and c comma 1 is also f. So we are getting f comma f. Similarly, f comma f is also not present in this table. Since both the pairs are not even present in this table, so we will not mark d comma c. And since these two pairs are not even present in this table, that means d comma c can never be marked in this particular table. So d comma c will always left unmarked in this table. So even if we calculate iteration number 2, iteration number 3, iteration number 4 or so on, d comma c will always be unmarked. Let's check the next unmarked pair, which is e comma c. So we are getting e comma c and for this we will write delta e comma 0, delta c comma 0. Now e comma 0 is e and c comma 0 is also e. So we are getting ee. Again ee is not present in our table. Let's check for the input symbol 1, delta e comma 1, delta c comma 1. E comma 1 is f and c comma 1 is also f. So we are getting f comma f. Now f comma f is also not present in our table. Since both of the pairs are not present, so they will never be marked in our table. So we will not mark e comma c. Like d comma c, e comma c will always be unmarked in this table. Let's check the last unmarked pair for the first iteration, which is e comma d. E comma d. So for this we will write delta e comma 0, delta d comma 0. Now e comma 0 is e and d comma 0 is again e. So we are getting e comma e. Again e comma e is not present. Similarly for the input symbol 1, delta e comma 1, delta d comma 1. So e comma 1 is f and d comma 1 is again f. So we are getting f comma f, which is also not present in our table. So we don't have to mark e comma d, which means d comma c, e comma c and e comma d. These three pairs will always be unmarked in our table. So in this way we have done with our first iteration. Now let's move towards the second iteration. The first unmarked pair is again b comma a. So for b comma a, we have already understood these transitions. and we are getting A, B and D, C. A, B is unmarked and D, C is also unmarked. That means B, A will not be marked. Now the next unmarked pair is D, C. And I have told you that D, C can never be marked because E, and F, are not present in this table. So we will not mark D, C. And in examination, you don't even need to write D, C in second iteration because earlier you need to mention that D, C will be always unmarked in our table. Similarly, for the next pair, which is E, C, both E, and F, are not present. So we will not mark E, C. And for the pair E, D also, we will not mark E, D. So this is the final table after iteration 2. And since we are not getting any new mark in iteration number 2, that is why no further marking is possible. That means we are done with our step number 4. And after step number 4, this is the table that we have got. Now let's move towards the step number 5. Combine all the unmarked pairs and make them a single state in the minimized DFA. So we have to combine all the unmarked pairs. These are the 4 unmarked pairs. So the unmarked pairs are B, A, this one, D, C, this one, E, C, this one, and E, D, this one. So these are the unmarked pairs. And we need to combine the states of these unmarked pairs to get the single state of our DFA. So the states of the minimized DFA are AB, because BA is combined together to form a single state which is AB. Now why we are getting CDE? Because D is getting combined with C, and E is getting combined with C, and E is also getting combined with D, which means overall C, D, E are combined together. So we are getting the resultant state as CDE. So A and B are combined together, C, D and E are combined together, and the remaining state is F. So the 3 states of the minimized DFA are AB, CDE and F. So these are the 3 states of the minimized DFA, and this is the original DFA. Now we need to make the transition diagram of the minimized DFA containing these 3 states. So the 3 states are AB, CDE and F. AB is the initial state, CDE is the final state, and F is just a regular state. Now why AB is the initial state and CDE is the final state? Because the initial state of our original DFA is A, and the state containing A is only this one. That is why AB is the initial state. And C, D, E are the final states of the original DFA. So any state containing at least one final state of original DFA will be the final state of the minimized DFA. Fortunately, we are getting all the final states in only one state. So CDE will be the final state of our minimized DFA, and F is just a regular state of our minimized DFA. Now let's complete all the transitions. First for the state AB. Now here, A on 0 gives B and B on 0 gives A. But in this minimized DFA, A and B are not the single states. So collectively we can say AB together on 0 gives AB itself. So we will simply create a self loop of the input symbol 0 over the state AB. Now we need to calculate AB on input symbol 1. So A on 1 gives C and B on 1 gives D. So A and B on 1 gives C and D. But CD is not a state in this DFA. We have the state CDE which contains CD. So AB on 1 gives CDE. Now we need to calculate the transitions for the state CDE. C on 0 gives E, D on 0 gives E, and E on 0 gives E. But E is not a single state in this DFA. So we can say CDE on 0 gives itself. Now, C on 1 gives F, D on 1 gives F, and E on 1 gives F. That means CDE on 1 gives F. So we can say CDE on 1 gives F. Now F on 0 gives F and F on 1 also gives F. So we will simply create a self loop of the symbols 0 and 1 over the state F. This is the transition diagram of minimized DFA. So originally we were having 6 states, and in the minimized DFA, we are having only 3 states. In this way, we have minimized this DFA using the table filling method or Myhill-Nerode theorem. In this way, we are done with our topic, Myhill-Nerode theorem. In the next lecture, we will solve one more problem on the table filling method. So this was all from my side for this lecture. Thank you, and I'll see you in the next lecture.